Okay, class, welcome to lecture 25. Today we're going to talk about countably infinite and uncountable. Um, so last time we already started this sort of. Last time we learned about countably infinite. So we learned a set S, what it means for a set S to be countably infinite. It's called countably infinite. If the idea is that it has infinitely many things in it, but at the same time, I can pair them up with the natural numbers using a bijective function. So what this really says is you can like sort of line up all your elements in S in the same way that the natural numbers are lined up 0, 1, 2, 3, 4. You can line up all the elements in S and pair them up. And if not, then it's called uncountable. So if S is infinite or has infinitely many elements, but for some reason there is no bijective function, there does not exist a bijective function from n natural numbers to S, then S is called uncountable. The idea being that now you cannot make this pairing with the natural numbers. So it's sort of like S is so big that you're unable to list them all one at a time like you can do with the natural numbers. So hence you're unable to count them. That's one way to think about it. That's why it's called uncountable. And then what else did we learn? We learned some extra fancy words. So the cardinality of the natural numbers is called aleph naught, which I'm going to keep writing as a sub 0. So it's not a number, it's just this is what we define to be the cardinality of the natural numbers, but it is called, this is not so important, it's an example of a cardinal number. That's what some people call it. You should think of it as sort of like the first infinity, the first level of infinity that you learn about. It's like the smallest cardinality of an infinite set, which implies that something bigger is coming, and that's exactly what's happening. But first, we're going to prove some more facts about countably infinite sets before we move on. So let's prove some, just to give us more practice, some more facts about countably infinite sets. So last time we proved a few. We proved Z was countably infinite. The positive rationals were countably infinite by proving that there was a function from the natural numbers to those things. That was bijective. But let's think of some more interesting facts. And then they'll allow us to create more examples. Okay, so here is a cool theorem. If you have two countably infinite sets, well, you might want to think about what can happen if I union them together. But first, let's just assume that they have nothing in common in the first place. So it's more interesting when I union them together. So a way to say that is that the intersection is the empty set. So I have these two sets with nothing in common. They're both countably infinite. if I union them together, it turns out to still be countably infinite. Meaning it's not so big that I can no longer pair up natural numbers with the union, which is very weird because it seems very strange because I'm pairing up A, I'm able to pair up A with the natural numbers because it's already countably infinite. I'm able to pair up B with the natural numbers because it's countably infinite. And then somehow if I union them together, I'm still able to do that, even though A and B were already taking up all the natural numbers in a perfect pair. But that's the interesting part about infinity, is stuff like this can happen. Okay, so let's prove it to make sure it can happen. So we're starting off with A and B being countably infinite. And we're just going to work with what that means. Well, I guess we also have that the intersection is the empty set. Sorry, why did I write not equals up here? I want it to be the empty set because that means they have nothing in common. So that when I union them together, it's more interesting. Okay, so then we know this. What does this really mean? Well, what does it mean to be countably infinite? It means that there's a function from the natural numbers to A, which is bijective. And again, you really want to keep thinking about bijective as a function which pairs everything up perfectly with no overlap, and everything is accounted for. But B is also countably infinite, so there's another function from the natural numbers to B, which is also bijective. So we don't really know what A and B look like, but the basic idea is that, I'll just do it on scratch work. The basic idea is that because of this bijection, what I'm secretly implying is that all my elements of A correspond to natural numbers. So I can sort of think of them as secretly being a bunch of A's with indices, subscripts, just indexed by the natural numbers. And I have this function that pairs them up perfectly. And then the same thing happens with B. So what we're going to do is we're going to reason with pictures first using this stuff. Okay, so the idea is that the bijective function really means that there's just this pairing up of elements in A and elements in the natural numbers and elements in B and then elements in the natural numbers. So now I'm going to stick A and B together somehow. I'm going to union them. So how can I still pair everything up if I do that? Well, I can sort of just slip in, people call it, say like you slide into your DMs. Well, we're just going to slide B into A's DMs. So I'm going to stick B0 in between A0 and A1. I'm going to stick B1 in between A1 and A2 and so on like that. So what I'm really doing is I'm thinking of A union B as this set, which I can still write as a list, and that's the whole idea behind countably infinite. But now the list looks like this. And then my natural number pairing is just the same as before, except I just had to move everything over and so on like that. That's going to be the idea behind the function that we create right now. And in pictures, I hope it's not so bad. This is how the bijective function will look. But when we actually go to define it, it looks a little bit harder. Okay. So let's define it. So I have to define a function like this and show it's bijective. So whenever we get stuff like this, the idea is secretly a piecewise function. So the idea is like, if you're dealing with an element of A, do something. If you're dealing with an element of B, do something else. And that's exactly what's going to happen over here, except the problem is we don't really know that these are the names of the elements in A and B. I was just using this as a little mini example. So I can't do that. But what I can say is that there's a function. This is a function f and g. So what I can say is, well, I don't know that this is called a0, but I do know that it is f of 0, because that's f of 0 is something in A. And then this would be like f of 1. And over here, this would be g of 0. And this would be where 1 is getting sent by g. So the elements in A and B do have names. They're just named in terms of the natural numbers and where they're sent. So that's what we're going to use to decide on how H works. Okay. So here it is. Define this by H of a natural number. Well, let's see. If I want to hit all of A and B, then my function has to use f and g somehow. And over here, the hint here is that I should think of it in terms of evens versus odds. So what I'm going to do is I'm going to say my function h is going to be determined. It's going to be dependent on whether n is odd or n is even. And what am I going to send n to? Well, if n is odd, I'll just send it to f of n minus 1 over 2. But if n is even, I'll send it to n over 2. And we can see that that's basically what's happening over here. I may have flipped f and g, but the idea is that the evens, so 0, 2, and 4, are being associated with f of half of that number. So this would be 2 over 2, and this would be 4 over 2. Whereas when it's odd, it's being associated to g of n minus 1 over 2 of that. So that would be g of 0. This would be g of 3 minus 1 over 2, which is g of 1. And that's exactly what's happening. So I think I flipped f and g, but it doesn't really matter which one comes first over here. So I'll leave it like this. Okay, but in the proof, I'll just say exactly how the mapping is working. So if this is the function, then let's just see how everything is mapped. So what's h of 0? H of 0, well, 0 is even, so it's g of 0 over 2. So it's g of 0. Okay. H of 1, what is that? Well, that's 1 is odd. So it goes to f, it uses f. 1 minus 1 is 0, so 0 over 2, 0. So what we're going to see is this pattern. So you should fill in the blank here, but this is what the function does. And it just keeps going like this. So what we want to notice is that on this side, all the elements of A and B are accounted for because G of every, oops, I skipped 3 for some reason. Sorry, I skipped 2 even. So what we want to notice here, same color. What we want to notice here is that these red stars are suggesting that all elements of B are accounted for. And these blue stars, because this pattern will continue forever, suggest that all elements of A are accounted for. So here, all elements of A union B are assigned something from the natural numbers. So here are my natural numbers, 0, 1, 2, 3, 4, 5, and so on. Each natural number will go to an element of A union B because F and G are bijective, then this list these are just all the elements. This is really just the set B. And because F is bijective, these elements really are just the set A. So what this is saying is that this function, no matter what element of A or B you look for, you'll hit it with something eventually as you go down further. And that tells you that H is surjective. And the list doesn't ever repeat on the right, so it's injective. So this is a bit of an informal proof. But I hope that you just get the idea down behind what we're doing. Okay, because now we want to use this theorem to say something more interesting. So last time we showed that the positive rationals, oops, should be a plus up there, was countably infinite. So I hope you can believe that the negative rationals are also. And then in the lecture problems, we showed that if you just throw in one extra element, so I'll just throw in 0. If I union a single element to an countably infinite set, it stays countably infinite. So because of the theorem, we can now conclude that the rationals are also countably infinite. Because the rationals you can think of as, well, it's the positive ones union the negative ones, oops, union 0. Okay, and if I union countably infinite sets together, the result is still countably infinite. So the basic idea is that unioning 2 infinite sets together that are both merely countably infinite is not enough to create a big enough set that's uncountable. So we still have not seen any uncountable sets. So now we're finally going to do that. So let's find an uncountable set. The super weird mystery will be solved. So a good guess is R. the real numbers. Well, you don't have to even use all of R, actually. So we're going to zoom in on a smaller subset of R. We're just going to look at the numbers from 0 to 1. So all the real numbers, though, not just some of them, but every single one between 0 and 1. So people call this the open interval from 0 to 1. So you can also say it like that. It does not mean the coordinate 0, 1. Unfortunately, we reuse the same notation. So this is also called the open interval. 0 to 1. So the point is, it's all the numbers from 0 to 1. You could think of it on a number line. Here's 0, here's 1. You often draw it like something like this, or something like this. It's all the numbers in between. Every single number you could imagine. So we're gonna just focus on that set. A couple of little facts before we prove it's uncountable, just that'll help us with the proof. If you have a number from 0 to 1, aka a fraction, well, then it has a decimal expansion. So what I'm going to do is I'm going to use, well, if I want to be very arbitrary, then I don't know what each decimal is. So I could say like, okay, I'll say that the 10th place is X, the 100th is Y and Z. But then the problem is it's only 26 letters. So I'll just run out of letters if I try that. So instead we say, this is where subscripts are the best. A1 will just mean the first decimal place, and then A2 is the second, and A3 is the third, so on like that forever. So every fraction has, between 0 and 1, has a decimal expansion like this, where each AI, meaning any arbitrary digit, decimal place is a digit from 0 to 9. So for example, 0.3257.6. That's something like this. So the first A1 is 3, A2 is 2, A3 is 5, and so on. A4 is 7, so on like that. So I hope you can believe this little quick fact that every number between 0 and 1 has a decimal expansion like that. So then, when are two decimals the same? So two numbers A and B in between 0 and 1 are equal when, well, A has a decimal expansion, B has a decimal expansion. So when would they be equal? Well, only if every single decimal place is the same. So they're equal when A1 equals B1, A2 equals B2, and so on like that forever. Okay, so this is going to come in handy later. One minor annoying fact that perhaps your high school teacher famously said to you a long time ago as some really cool fun fact, some real numbers have two different decimal expansions. Huh? It's not so crazy. If it ends in a bunch of 9s, it's the same as ending in a bunch of 0s in a different way. So for example, very most famous example is this one. 0.9999 forever is the same as 1.0000. But this holds for any thing that ends in a bunch of 9s. As long as the 9's going forever, I can actually write it with a bunch of 0s instead. So what we do is we just think like, okay, we're just going to stick with one decimal form. We're going to call this the real one that we actually count as the unique decimal expansion. Okay. All right, so with all these little fun facts, we're now ready for the theorem. The open interval is finally uncountable. So just intuitively speaking right now, what this means is that I cannot list all the numbers from 0 to 1 in a way that they get paired up with the natural numbers. And just to get your idea, the idea behind why this is true, it's because if I start trying to like list them all, I'll say, okay, I'll list, here's the first one, 0.1. Here's the next one, 0.2. Well, just by doing that, I've already skipped an entire infinite amount. Just by doing that jump. So then you say, okay, I jumped too far. I'll do this, and then I'll do this. Oh, sorry, that's not what it would be. It would be something like 0.11. But then even then, you've skipped so many. Oh, why do I keep writing a second decimal? There. No, now that's no decimals. There. Okay. Even that step, if you're just trying to list them all out, you've already skipped infinitely many again. And there's just no way around this. And that's the basic idea. But the proof is much cooler. So, okay. It even has a fancy name after the person who came up with it. This proof is often called Cantor's diagonalization argument, named after a mathematician named Cantor, who thought about infinity so much that he went mad. So you have to be careful about doing that. Okay. So first, we want to establish one thing, that this set actually has infinitely many things in it in the first place. So first off, the interval from 0 to 1 has as a subset an infinite set. So like, just pick your favorite one: a half, a third, a fourth, a fifth, forever. So this is a subset of the interval 0 to 1. So since 0, 1 contains infinitely many things already, just from that, we know it's an infinite set already. So we're not trying to figure out if it's infinite or not. We're trying to figure out if it's uncountable versus countable. Now we know it's infinite. So once it's infinite, then it's either countably infinite, or it's uncountable. So, okay, so we're trying to show it's uncountable. So let's do that. But how? Well, by showing it's not countable. We'll show it's uncountable by showing, what does it mean to be countable? That there's a function from the natural numbers to the set that's bijective. So we're going to show that there is no such function. There does not exist a function from the natural numbers to the interval, which is bijective. And we're going to do it in a very sneaky way. A couple of sneaky tricks. The first trick is super interesting. So one way to do this is to assume, or to show that if this guy was, if there already was an injective function, then it cannot be surjective. Why does this prove that no bijective function exists? Why does that show what we want to show? Well, because what we're saying is that being injective and surjective at the same time is incompatible for any function from the natural numbers to the interval 0, 1. And so if a function cannot be injective and surjective at the same time, then that means it can never be bijective. So that's the trick. Okay. So that's what we're going to do. This shows no bijective function exists. Because if it was bijective, it would be injective, but we've shown that, we're going to be showing that when it's injective, it can't be surjective. So it can never be both. Okay, so to do this, we suppose f is injective. And show it's not surjective. So now I'm just rephrasing things over and over, sort of, to try to make the proof more clear. Okay, so how do I show something is not surjective? Well, I have to show that not everything in 0, 1 gets hit by the function. So show this by finding an element in the codomain such that no matter what you plug in the domain, it'll never equal that element from the codomain, aka not every element gets hit, i.e., sorry, I should use little n's instead of x's just because it looks more natural number-y. So i.e., in other words, no natural number is assigned to y. Okay, so here's how we're going to do that. It's very tricky. This is the diagonalization argument. Here's how. What we're going to do is we're going to list all the elements. We list all fn's, meaning what are all the outputs of the function? Well, they just come from plugging in 0 and going down forever. Plugging in 2, plugging in 3, plugging in 4, you get the idea. So these are all the outputs of the function. They all live in 0, 1. So they all have decimal expansions. And so I'm going to write decimal expansions for each of them. But now we're going to have to use a double indice. And here's why. So this guy, if I wanted to call it like I did before, A1, A2, A3, and so on, well, then the next guy, I can't use the same letters because then it would imply it's the same exact number. So I'd have to say like, okay, B1, B2, B3, B4. That way it's different. But what's the problem there? Then you run out after 26. There's only 26 letters. So instead what we do is we use double subscripts. So the first decimal of the first output will be A11. And the next decimal, I'll just shift the first guy over. It doesn't really matter, or the second guy. I think I decided on the second guy. So it'll be A12, then A13, then A14, and so on forever. And as I go down, I'll shift the first subscript A21, and then this will be A22, A23, A24, 0 point. So this will be A31, A32, A33, A34, and so on. So I hope that you get the idea. Okay. So then in general, Fn, how does Fn look in general? It looks like 0.an, because as I go down, n, the first indice changes. So an1, an2, an3. Eventually I'll hit ann. That's going to be a key factor. This is why it's called the diagonalization. So we're going to keep our eye on these guys as we continue on. Okay, so in any case, what we've done here is we've listed all of the outputs of the function in decimal form. And what we're going to do is we're going to show that there is a number which is not in here. So we're going to show there exists a y not in this list. So that would show you that there's no output that hits this y because all the outputs are listed here on the left. So we have to create a new number that's not in this list. That's 100% sure not in this list. Okay, so here's how. Let's construct some y. I'm going to use a new letters. So B1, B2, B3, such that y does not equal f of n for any n. Okay, aka it's not in the list. So here's how. We're just going to choose each decimal place one at a time in a very smart way. So I'm going to choose B1. First of all, I'm not going to ever pick zeros or nines because I don't want to have this annoying repeated zeros or repeated nines business. So B1 cannot be 0, it cannot be 9. But then what I'm going to do is I'm going to say it cannot be A11. So what I'm doing is I'm setting up a situation where the first digit will just be not this guy and also not 0 or 9. The second digit will not be this guy. The third digit will not be this guy, and so on forever. The nth digit will not be this guy, and that'll do it. So let's see it. Okay, so just to rephrase it, so choose B2 to not be 0, not be 9, and not be A22, and so on like this. Okay, so let's do it. So how can I make a number like this? By where b sub I, so I'm just saying in general what the ith decimal place will be. Well, you could pick whatever you want. So what I'm going to say is it's going to be a 7 if the diagonal entry is 5. Because what I want is I always want this to not happen. I want B1 to not equal A11. I want B2 not to equal A22. So what I'm asking for is I want this first digit to definitely not be the same as A11. So how can I ensure that? Sorry, these should be II. Well, by picking this rule. If it happens to be 5, if A11 was 5, then I'll put a 7 there. But if it's not 5, then I'll put a 5 there. So what this ensures is that this, so for example, if the first digit A11 of the first number in the list, if it was 5, then B1 would be 7. But if it wasn't 5, then B1 would be 5. So the number defined in this way is not in this list because no matter what natural number you go down to, so you could go down to 50, you go down to 1,000, you go down to 1,000,000, no matter what, it's going to have at least one decimal place which is different than this fancy number y. So no matter what, f of n will not be y, since y and f of n will differ automatically by the definition of y at the nth decimal place. So you go down and you say, I bet y is right here. This is y. Well, then I go down to A44 and I say, but A44 is a 5. And the fourth decimal place of y is automatically not a 5, it's a 7. So that means y is not this guy. They're not the same number. And no matter what, that'll always happen. You go down to 1,000 and you'll say, aha, f of 1,000, that's definitely y. I gotcha. But then I'll say, no, go to the 1,000th digit, A1000, 1000. And oh, it's 7. Well, guess what? B1000, the 1,000th digit decimal place, is 5. So no, y does not equal f of 1,000 because they differ there. So that's why none of these numbers are y. So y is not in this list. 5 and 7 are arbitrary. I could have changed these, and I could have changed this as well. So in fact, there's lots of numbers that are not in that list. Okay, so that proves it. So this shows f is not surjective. So from all the setup I did at the beginning, all this work is telling us that 0,1 is uncountable. And that's what we wanted to show, right? So this leads us to some fancier notation. So the cardinality of the interval from 0 to 1, which is sort of like how many elements are in there. Well, it's not aleph not, because we just showed that the natural numbers are not isomorphic to 0, 1 by showing that there's no bijective function. So it has a different cardinality, and we just call it something else. So we call the cardinality of 0, 1, just call it C. And it stands for continuum. Continuum, I don't know how to spell it. No, that's not right. Continuum. The idea is that the continuum, very fancy sounding word, it's sort of like the line. if you keep zooming into the line, you're just like not getting anywhere. It's just like this continuous thing. So 0, 1 has the cardinality of the continuum, but it's just a fancy word. But it really, the point is that it's not the same as the cardinality of the natural numbers. And in one sense, we think of it as bigger because it can't make a bijective function. So it's, instead of being countably infinite, it's uncountable. Okay, so then we use this to define sort of the next level of infinity. So what we do is we say like any set A where A is isomorphic to 0, 1 has the same cardinality. So you say that the cardinality of A is also C. So it's just like for natural numbers, any guy that's the same, that's isomorphic to a natural number, meaning you have a bijective function, tells you that the cardinality of that set is Aleph naught, because that's the cardinality of the natural numbers. Okay, so it's the same idea here. So 0, 1 is very big. All the numbers from 0 to 1. So intuitively speaking, so like people might say something like this: there's more numbers between 0 and 1 than there are rational numbers. This is the intuition behind cardinality. Cardinality is a measurement of size. And so what we're saying is that the rational numbers, they're not even that big. They're countable. But the real numbers are super big. Even if you only look at the real numbers between 0 and 1, the cardinality, the size of that set is already bigger than the rational numbers. You don't even need all the real numbers. You just need the ones between 0 and 1. That's how many real numbers there are. And then just little extra facts you can show about uncountable infinities are having to do with like what other sets are also uncountable. So let's do that next. So any open interval doesn't have to go from 0 to 1. It could be from your favorite number to your second favorite number, as long as they're in the right order. That's also uncountable. And so the cardinality is still C. It doesn't get any bigger if you increase the size of the interval. So 0, 1, the cardinality of that is the same as the cardinality of 10 to 50. It doesn't get any bigger by doing that. And the proof is not so bad, actually. So you just have to define a function to show a bijective function to show that they're the same size. So that's how we define size in terms of, is there a bijective function or not? So if there is, then we think of them as being the same size because that means they have the same cardinality. So let's define this function here. I'll define it for you, and you can check that it is bijective if you like. But here it is. So this function will work, and it'll show that they are isomorphic, so therefore they have the same cardinality. Okay, so this shows they're isomorphic, which shows what we want to show. Okay, so then lastly, the big finale, the real numbers are still just uncountable. And I say the word just because you can go bigger, but this is not there. This is not big enough to go bigger than uncountable. The real numbers are uncountable. And here's the proof. You just need a function from, well, instead of using 0, 1, now that we know any interval is also uncountable, I'll pick a different interval, negative pi over 2 to pi over 2. And I'll define it by this. You might not remember trig, but tangent of x goes from negative pi over 2 to pi over 2 to r. And you can show if you want, but you have to remember pre-calc stuff that it's bijective. I'm just going to take that as an assumption. So the interval from negative pi over 2 to pi over 2 is isomorphic to the entire real number line. So r is still uncountable. So there's as many real numbers between two numbers as there are total real numbers, is the idea, the intuition. In terms of cardinality, those sets are the same size. So some people say it like that. There are as many real numbers as there are real numbers between 0 and 1. In terms of cardinality, in terms of you're able to pair up every single real number with just the real numbers between two other numbers. 0, 1 doesn't have to be 0, 1. You can pick whatever you want there. So where does this leave us? We've seen two infinite cardinalities, the aleph knot and the continuum. So the idea is that one of them corresponds to the natural numbers, the other corresponds to 0, 1, or the real numbers if you want. And they're sort of the measurement of the size of these two sets. And so in terms of cardinality, real numbers are bigger than natural numbers. But then you would, of course, want to ask, are there bigger ones than C? Meaning, is there another set in which you cannot have a bijective function from the real numbers to that set? And the answer is yes. And in fact, even weirder, there are infinitely many of those, infinitely many different infinite cardinalities. So that's super weird. We're going to prove this in the lecture problems. Okay, so that's it for today. Hope you're still with me. This will be the end of infinity, I think, because we got other stuff to cover and it just gets a little bit too crazy. Okay, see you next time.